Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in applied electronics. We have been going through the section on interference. The contents of this lecture number 16 will be as follows: a brief recap, air wedge, conditions for constructive and destructive interferences, expression for fringe width. Now, in the brief recap, I have only 2 points which are to be recollected by you. When a light ray is incident from a rarer medium, if it is incident on a denser medium like glass, then it will undergo reflection, and in this process it will undergo a phase change by pi. This we have seen earlier, but on the other hand, this light beam or light ray will not undergo any phase change, because it is incident on the interface between denser and rarer, whereas from rarer to denser it will undergo a reflection. In this process there will be a phase change, which will be taken into account in our theoretical estimation of the bandwidth and other things. Then I also mentioned to you what is meant by the path difference. What do you understand by path difference? When you got 2 light rays which are travelling from slit 1 and slit 2, S1 and S2, the 2 slits, then the extra distance travelled by one of the light rays compared to the other light ray is known as the path difference. The extra distance travelled by one of the light beams. You see here S1 is here, the slit S1, S2 is here. Now, you draw a perpendicular, and this S2 to this particular distance delta L, or if this is D, if this is angle theta, then this will be your d sin theta, the delta L will be equal to d sin theta. This is the additional path, because this this line drawn from this point to S1 P and from this point to P, these two will be equal to one another. On the other hand, if you take the distance between R2 and R1, R2 is this much distance, right. The extra distance travel is so called path difference. Now, what we are going to see now, in this path difference, if there is a full wave, you see again you got a point A here, point B, something like your slit S1 and slit S2. The light beam is coming from the source A, and the another light beam is coming from the source B, and these 2 beams meet each other at this point C. So, the distance travelled by this light ray or beam is LAC from A to C, whereas this is LBC, B to C, right. If the path difference between these two, the path difference is this much, right. If this path difference is integral multiple of lambda of the whole wavelength means lambda, right. or integral multiple of lambda, 2 lambda, 3 lambda and so on, then what do you understand by this? If you get a trough here, you will be getting trough from the two sources. A trough is obtained from A, trough will be obtained from the light beam coming from B also. If a crust is coming from A at this point, again a crust will be coming at the same point, because the path difference is lambda, right. Okay. So, this should be understood. If the path difference is lambda, then a crust will be meeting a crust, or a trough will be meeting a trough, leading to constructive interference. This point should be well understood. If the path difference is lambda or 2 lambda or 3 lambda or integral multiple of lambda, then it will lead to constructive interference. On the other hand, you look at the following picture. In this picture, you have got a crust here, and here the path difference is lambda by 2, right. The path difference here, the source A is half a wavelength further from B, then the path difference will be 1.5 times lambda or 0.5 times lambda or 1.5 times lambda or 2.5 times lambda. So, it is n plus 1 into lambda by 2 or n minus 1 into lambda by 2. If that is the case, then a crust will be meeting a trough. A crust is a upward displacement, trough is a downward displacement, as all of you know by now. So, that will lead to a destructive interference. This point should be borne in mind. Okay. Then we are talking about the colors of thin films, why the soap bubble acquires a color, or a petrol vapor which is on the top surface of a film of water, why does coloration occur? All these things are due to the phenomenon of interference, and we were discussing in the last lecture a thickness of a oil film or the glass plate of thickness T. This may be the thickness T may refer to the film of a different refractive index mu, and you have an incident beam here getting reflected, then the part of the light beam goes along this direction q s, comes to this point u and travels to goes along this direction. Now, we are talking about the two beams n r and u v and how they will be interfering. This interference, will it lead to a bright fringe or a dark fringe? Will it lead to a constructive interference or a destructive interference? That is what we have seen in the last lecture. That means, how much is the path difference? You see, from after n and u, there is no path difference, right, because n u is perpendicular, right. N u is line drawn perpendicular to q r. So, after that there is no path difference. Here the one of the light beams travels through a distance q n, whereas the other light beam passes through q s plus s u, but this multiplied by mu, because this is taking place in a medium with the refractive index mu. Therefore, we got the path difference in the earlier lecture, that turns out to be, you have the Snell's law, the refractive index will be mu times sin I by sin r, and we got in the last lecture we showed that q n to be equal to 2 t into sin I into sin r by cos r, and that will be equal to x, that is the path difference. The path difference which I have been mentioning now will be equal to mu times 2 t by cos r minus mu into 2 t by cos r multiplied by sin square r. Now, taking this outside, you get inside the bracket 1 minus sin square r, that will be equal to cos square r. Cos square r divided by cos r will be equal to cos r. So, the final expression will be the path difference between the two light beams will be simply equal to 2 mu t cos r. So, the ray q r is the reflected ray and the ray u v is the transmitted ray. So, the path difference works out to be 2 times mu t into cos r. Now, what is it we have not taken into account? Now, we have not taken into account the fact that one of the light beams suffers a phase change, because it tries to go from air into a medium which has got a refractive index mu. The medium may be an oil film or something else. So, that is to be taken into account. When you take that also into account, the effective path difference becomes equal to, let me now repeat, due to reflection there is a phase change of pi degree or an additional path difference of lambda by 2 that will be introduced. So, the total path difference becomes equal to 2 mu t cos r minus lambda by 2. Now, what should we do now? If this path difference becomes equal to integral multiple of lambda, then what will happen? That is the condition for constructive interference. As I told you in the beginning of the lecture, if the path difference is equal to lambda or 2 lambda, that will the condition for constructive interference, or you will get a bright fringe. So, the path difference now, to get the condition for a bright fringe, the path difference should be equated to integral multiple of lambda, that is what we have written here. So, 2 mu t cos r minus lambda by 2 that we evaluated now, this is what we had, that is equated to n lambda, that is the condition for constructive interference, or in other words that can be rewritten as 2 mu t cos r to be equal to 2 n plus 1 by 2 into lambda, taking lambda to the right hand side of the equation. So, the final condition that you obtain that has been blocked, it shows that the condition for constructive interference or getting a bright fringe is the following, namely 2 mu t cos r should be equal to 2 n plus 1 by 2 into lambda, that is the condition for constructive interference. Now, you can visualize or you can try to understand by yourself what should be the condition for destructive interference. I told you in the beginning, if the path difference is lambda, 2 lambda etcetera, that is the condition for constructive interference. On the other hand, the path difference is lambda by 2, 3 lambda by 2 or 5 lambda by 2, that is the condition for destructive interference, because lambda by 2 means when a crust is coming, a trough will be coming. So, therefore, now I can write down the condition for the dark fringe, this is the condition for a bright fringe. So, the condition for a dark fringe will be as follows. The condition being 2 mu t cos r minus lambda by 2 that we had earlier. Instead of equating that to be equal to n lambda, what we should do now, it should be equal to 2 n minus 1 into lambda by 2, that eventually leads to 2 mu t cos r to be equal to n lambda. So, if 2 mu t cos r turns out to be n lambda, where n is an integer, that is the condition for obtaining a dark fringe or a dark band. Above equations that we had just now, they give the conditions for bright and dark fringes produced by thin films due to interference of light. So, we have arrived at the general conditions that should be satisfied by a film in order to obtain a bright fringe and a dark fringe. Let me go back. If you have a film of thickness t and the film has got a refractive index mu, the thickness is t, mu is the refractive index, then r is the angle of refraction, that should be equal to integral multiple lambda, that is the okay. From this is the thing that you have now, the conditions for constructive and destructive or obtaining the bright and dark fringes produced by thin films due to interference of light. Now, these conditions are to be applied to the case of an air wedge. What is an air wedge? We will see air wedge is nothing but you have two glass plates. You have got a plate like OP, OP is a glass plate, right. Then OQ is another glass plate. You keep one of the glass plate like this, another slightly inclined, right. How do you produce the two glass plates? How do you make this angle theta here? You can put a sheet of paper whose thickness is to be measured. You can imagine the thickness of the paper cannot be measured by a Vernier caliper or a screw gauge. So, this air wedge is a can be considered to be optical instrument to measure the thickness of a thin wire or the thickness of even hair can be measured by not by means of a barrier caliper or by a screw gauge. Using the phenomenon of interference, the thicknesses of thin materials in the form of paper or a wire, those things can be measured. That is what we are going to do at a later stage. Prior to that, we are talking about how you produce a wedge shaped film. That means you have to interpose a wire. You insert a wire and you got a glass plate here, then you have a piece of paper upon which you have the other glass plate. This theta has been exaggerated, but it will be very small. Theta will be, because the thickness of film paper is very small or a wire will be very small. So, theta will be very small. This is an exaggerated thing in order to make you to understand the phenomenon. Okay. So, consider a wedge shaped film of refractive index mu enclosed by two plane surfaces OP and OQ inclined by an angle theta. Okay. The thickness of the film increases from O to P. You know the film thickness, this is the film. Here what do you have? You got air as the medium, right? You got a air as the medium. The thickness of the film that we are talking about, here you got air, that increases obviously from this region to this region, that we will talk about in detail later. So, when a film is illuminated, when this is the film, right, you got a air as the medium, when this film is illuminated by a parallel beam of a monochromatic light, interference occurs between the rays reflected at the upper and lower surfaces of the film. What is the upper surface? The light coming from here will undergo reflection at this point, the light beam will go in this direction, the part of the light will undergo fraction, it enters in the medium air, it is again reflected by this glass plate at a point C, it emerges along this direction C D and then comes back into the medium air in this direction, it goes along this direction D E. The two light beams A B and D E will be interfering. You understand, the light beam A B and D E will be interfering with each other. Now, we have to find out what is the resultant. The conditions that we obtained earlier should be applied here to find whether these two interfere, whether they lead to constructive or destructive interferences or lead to bright and dark fringes. Okay. So, the essential thing is we have to see the interference between the two light beams A B and D E. In the wedge shaped film we have been talking about has been exaggerated, and essentially we are trying to find the light rays A B and D E, will they interfere with each other and what will happen to the resultant, whether the interference will lead to constructive interference or whether they will destroy each other, and the conditions which we have seen earlier will be applied here also. That is the reason why we had the theory of the interference in a thin film. The theoretical expressions we obtained earlier will be applied here. So, now we have got equidistant alternate dark and bright fringes which are observed here when it is illuminated by, you can have a microscope. It is usual for the students who do optics in the laboratory, they will be seeing the bright and dark fringes using a microscope. These things will be placed on the bottom of the microscope. The fringes are parallel to the line of intersection of the two surfaces. The important point is the interfering rays are A, B and D E, right, that is the important point. The rays A, B and D E, they will be interfering with each other and they emanate or originate from the same incident ray S A. S A is the incident ray. Now, A, B and D E are the rays about which we should be concerned with. Now, the fringes which I have been talking about will appear like this. Again, this is an exaggeration. You have got a bright band or a bright fringe a dark fringe, a bright fringe, a dark fringe, bright and dark alternately, right. This is a side view. As I told you how to get a air wedge, I told you about angle theta and all, right, the theta. What do you interpose? What do you insert? You have to insert a wire, right, a wire or a piece of paper, so that you get a inclination. You got a glass plate, another glass plate, between which you have to interpose or introduce a wire or a paper or some film whose thickness cannot be measured by other methods. So, this is the best method with a greater degree of accuracy. The thickness of the material can be measured. The interference fringes in an air wedge are regularly spaced, as is shown here. You have got a bright, dark, and the distance between the two bright bands is called the bandwidth beta. What is bandwidth? Distance between two bright bands. It will be equal to the distance between two dark bands also. Between the two dark lines or dark bands, this will be equal to beta. Similarly, from this center to this center, that will also will be equal to beta. What is beta? Beta is the bandwidth, which we will be using hereafter. Beta will refer to the bandwidth. Obviously, you know what is the fringe width or bandwidth is the following, right. The side view, in the cross sectional view, you see the cross section of wire that is introduced in order to obtain a wedge shaped film. The expression for the fringe width, that is what we are going to now obtain. The important thing is the expression for the fringe width. The condition for a dark fringe that we saw got it earlier will be 2 mu t times cos r, that will be equal to n lambda, n is an integer. Here for air, you got air here, right, you got air, mu is equal to 1. For normal instance, cos r will be equal to cos theta, that will be equal to 1. Suppose the nth dark fringe is formed where the thickness of the air film is T m, that is you got m here, right. The thickness of the film is T m. T m refers to the thickness of the air film. You got a air gap. The gap, as I told you earlier, the thickness of the film increases from this point to this point. As you go up, right, you got a wire whose diameter is d here. You are inserting a wire, right, to get a wedge shaped film, and T m is the thickness of the air gap, that is obtained at x m. X m plus 1 is the point where the thickness is T suffix m plus 1. What is T suffix m plus 1? You get the m plus 1th band at this point. T m is the thickness at this point x m, where you got a mth band. D is the diameter of the wire, L is the, you see the D here, the diameter of the wire, L is the distance between the point O and to the center of the wire. Okay, you got a wire here, the center of the wire, that makes the angle theta, right, that is important. That is the angle theta is made because of the insertion of the wire, and so the distance between O and the center of the wire is your L, and other things are known by now. So, you now know what is happening at x m and x m plus 1 at these points, at these distances. You get the m plus 1th and mth dark fringes from O. The point to be understood is x suffix m plus 1 and x m are the distances at which you observe m plus 1th and mth dark fringes. Okay. You know the condition for darkness. So, you get the mth fringe and m plus 1th dark fringe at for these thicknesses. The thicknesses are T m and T suffix m plus 1. Let me now write down the conditions. So, 2 times mu is 1, right. Let me go back, mu is 1, that is the reason why I put 2 multiplied by 1 into T. I may put T m or T suffix m plus 1, as the case may be. T m, the mth band, T m into 1 cos r, that will be m lambda. So, 2 T m will be equal to m lambda. Suppose the m plus 1th dark fringe is formed where the thickness of the air film is T suffix m plus 1. T suffix m plus 1 is the thickness of the air gap at which you have got the m plus 1th band. For the m plus 1th band, you will be having 2 times the same thing should be followed, 2 times T suffix m plus 1 is equal to m plus 1 into lambda. This is for the mth band, this is for the m plus 1st band, m plus 1th band, that is the mth band, this is the m plus 1th band. So, now you subtract these two. So, you get the mth band, m plus 1th band, the distance that separates the two successive bands will give you what? Will give you the bandwidth. Okay. That should be understood. What is bandwidth? The distance that separates two dark bands or two bright bands is the bandwidth. So, now I have got the mth band here, m plus 1th band here. Subtracting these two, I will be getting an expression of this kind. Now, we will move on to the summary session. A wedge shaped film is formed when one glass plate is kept inclined with respect to the other by having a thin wire being inserted or any other material being inserted between the two glass plates. You get a wedge shaped film. Bright and dark fringes are obtained depending on the thickness of the film, and the equations governing have been derived. Expression for the width of the fringe is obtained. Air wedge experiment allows one to determine the thickness of thin material. This is important. The questions are: what is air wedge? Question number 2, mention the conditions for bright and dark fringes. With this, we come to the end of this lecture. In the next lecture, we will obtain the expression for the bandwidth and the thickness of the wire which is inserted and so on. Thank you.
Thank you.